never tried to record a whole
lecture. So yep, it's recording. So okay. Let's see how this goes. And this is actually one of my favorite topics. In a way, it's kind of like the climax of the course in a way, because it shows the most ingenious stuff about numerical algebra, but all semester long. Well, and also Thursday. So today, we're finishing up eigenvalues. So with the QR algorithm, whatever version we're on, so we do the Hessenberg reduction. And then we have our loop where we take the QR factorization of H and then multiply the factors in reverse order to do a similarity transformation. And all this takes order n squared floating point operations per iteration. The trouble is convergence is too slow. It takes too many iterations to reduce H to some sort of quasi-upper triangular form with 1 by 1 or 2 by 2 blocks. So the goal today is to speed that up. So what happens is, so as far as I can actually be more specific about how slow a convergence is. The convergence is, so the subdiagonal entry, row P plus 1, column P, goes to 0, because we want these subdiagonal entries in your Hessenberg matrix to go to 0 at the rate that's a ratio of eigenvalues, consecutive eigenvalues in the ordering. Because remember, lambda 1 is the largest, lambda 2 is the next largest, and so on. So if these two eigenvalues are close together in magnitude, so if that ratio is nearly 1, then we have convergence problems. So what we can do is, so our first change is use a shift. So what you do instead is you take H minus mu times identity. So mu is a shift. And we take the QR factorization of that. And then you multiply the factors in reverse order. And then you just put the shift back. So in both cases, your H gets overwritten with Q transpose HQ. That's something you can verify by figuring out, what Q transpose H is from the first line. That's a QR factorization. It's just that you have a different Q in each case. So and the reason why we can do a shift is it lets us change the convergence rate. Because now it's a ratio of shifted eigenvalues. So if you choose your shift right, so that now this quantity is much smaller than this. So in other words, mu is close to lambda p plus 1, for instance, then you can achieve much more rapid convergence. All right. Now the question becomes, how do we choose this shift? So to get some guidance on that, we're going to look at the very unrealistic case. Suppose that mu is an eigenvalue. Of H. So what happens in that case is H minus mu identity is singular. But if we use our assumption from I mentioned last time, if H is assumed to be an unreduced Hessenberg matrix, so all the subdiagonal entries are 0, that means it has rank n minus 1. So it has n minus 1 linearly independent columns. So in our QR factorization, R has this form. R, because Q is an orthogonal matrix, it's going to be non-singular. Therefore, R has to be singular. And what would look like, because you have n minus 1 linearly independent columns, is you end up having a row of zeros in your R. So then what you do is, whoops, sorry, that's supposed to be upper triangular, not Hessenberg. Okay, so now what happens is you multiply this by Q, and we know we can figure out what Q is going to do, because what is Q? From Hessenberg QR, it's just a sequence of n minus 1 column rotations. So it rotates columns 1 and 2, then 2 and 3, then 3 and 4. So RQ is going to have this structure. It's really weird to look on your screen, Stephanie. It's like everything's backwards. Whereas like on the Mac, I see it frontwards. Yeah. So. Oh, good to know. All right. Well, the novelty's nice. So what happens here is, because you're rotating columns, the last row is zeros at the start. It's still going to be all zeros. It's just going to be a Hessenberg matrix with a row of zeros. Okay. And then the last thing you do is you add the shift back, so mu times identity. And all that's going to do to the structure is, is put a single mu in the n position, and a subdiagonal entry, the last subdiagonal entry, has gone to 0. So that's the magic of using a shift. So when you shift by an exact eigenvalue, we have deflation. In one step. Okay. Now, of course, we're never going to have an exact eigenvalue to shift by, because what are we trying to compute? The eigenvalues. But what this tells us that is useful is, suppose mu is not an eigenvalue, but it's an approximate eigenvalue. So that means that the columns of h minus mu I are almost linearly dependent, which means in R, there will be something non-zero here, but it'll be small. And that will cause this subdiagonal entry down here to also be small. So what we can do is, if we get a reasonable eigenvalue estimate and try this out, then we can just keep, carry out a few iterations, and over those few iterations, drive this subdiagonal entry to 0. Okay. So let's take a closer look at that. So to summarize, if mu is approximately an eigenvalue, then in your new matrix, h and n will be approximately equal to the shift, And then the subdiagonal entry next to that would be at least near to 0. Okay, so which would then, and things because of this being small, that confirms that this is actually an approximate eigenvalue. That we can actually see that from the structure of the matrix. So, so what we can do is this guideline, the single shift strategy. That sets mu equal to the NN entry of your unreduced Hessenberg matrix. Now, so I'm going to look at an example. It's a 2x2 case where we have, suppose we go ahead and use this shift strategy. Then your H, after shifting, using the 2-2 entry, the new 2-2 entry is going to be 0. And you're going to have whatever entries up here. And let's suppose your subdiagonal entry here happens to be small, so epsilon. So then, after you compute your new Hessenberg matrix, that's G transpose HG, where this is designed to perform a QR factorization, and so it carry out a QR step, like described over there. It's just going to be but because of the 2x2 matrix, it's going to be a single Givens rotation. So what you get, so the multiplication details are carried out in the notes, is you get so for this Givens rotation, you have a cosine-sine pair. So your cosine-sine pair, your cosine is going to be A over the norm of this first column, A squared plus epsilon squared. And then your sine is going to be pretty small. It's epsilon over square root of A squared plus epsilon squared. So if I keep that in mind, the new matrix is going to be A plus BCS. Then we have BC squared minus epsilon. And then we have minus BS squared. And then minus BCS. But now if I want to write those, I want to get C and S out of the picture. So I need a little more room here. So the 1-1 entry will be A times 1 plus B epsilon over square root of A squared plus epsilon squared. The 1-2 entry will be B A squared over A squared plus epsilon squared, which is going to be roughly 1 if epsilon is small, so therefore this part will be roughly B, minus epsilon. So what that means is for epsilon small, the top row doesn't change very much. We get A and B. Now, and then the 2-2 entry, I'm saving the most interesting entry for last, minus BCS, that's going to be minus AB epsilon over square root of A squared plus epsilon squared. And then finally, the 2-1 entry, but what we're trying to make go to 0 is minus B epsilon squared over A squared plus epsilon squared. Okay, now, why is this interesting? Because the original subdiagonal entry is order epsilon. The new subdiagonal entry is order epsilon squared. So in other words, if you're already able to make that subdiagonal entry small by making a wise choice of shift, but by using the NN element as a shift, that subdiagonal entry will go to 0 quadratically. Now we've seen quadratic convergence before, well not in this class, but in other classes like Newton's method and so forth, like where the error is the square, related to the square of the previous error. So you get this really rapid convergence. So the number of correct decimal places roughly doubling from one iteration to the next. So what that means is you don't need many iterations to make a single subdiagonal entry go to 0. So if you're trying to find n eigenvalues, you would be using, hopefully, order n iterations to accomplish that. And since we've already made the iterations themselves faster, then we have an algorithm with reasonable efficiency for what it's trying to do. And I have an example in the notes. It's on page 184. And what happens to the 2-1 entry after performing a few iterations? So the first one is not really small, but then the next iteration, noticeably smaller. And then another iteration after that will be, and what will happen is, so it's already order 10 to the minus 5th after 3 iterations. After another iteration, it'll be in the order 10 to the minus 10 from a quadratic convergence. And then maybe just one more iteration after that, and that entry is essentially 0, so you can just move on. So you have to choose what your tolerance will be to decide when do you declare a subdiagonal entry to be 0 so you can move on to another one. Okay, so that's the single shift strategy. So where we see quadratic convergence. Okay. And actually, suppose we're dealing with a symmetric matrix that has only real eigenvalues. So you can always use this. For symmetric matrices, there's another way to choose a shift. It's called a Wilkinson shift. It doesn't work with, instead of using an n element, it takes that bottom right 2x2 block, is involving rows and columns n minus 1 and n, and it picks out the eigenvalue of that 2x2 block that is closer to the nn entry and uses that for the shift. And the Wilkinson shift for symmetric matrix gives cubic convergence, so you hardly have any work to do at all to pick off a single eigenvalue in that case. And also for symmetric, we have order n operations per iteration. If you're only looking for the eigenvalues, if you want the eigenvectors too, that's still going to be more expensive, like order n squared. So things are really nice for a symmetric problem. We can pretty much declare ourselves done in that case. But for unsymmetric matrix, we have to consider that the matrix may have complex eigenvalues. So the single shift strategy is not effective for complex eigenvalues. What would happen is you would see this subdiagonal entry not going to 0. So we have to rethink. Okay. So for complex eigenvalues, use what's called the double shift strategy. So what you do is you choose two shifts. mu1 and mu2 are the eigenvalues of this lower right block. It comes from rows and columns n minus 1 and n. And you use those as your shifts. So then you carry out two iterations that are similar to one iteration from before. So you shift by mu1, you compute the QR factorization. So even though I'm calling it u, but it's a QR factorization. then go ahead and multiply those factors in reverse order and add the shift back, so I'll call that H1. And then we do it again with the other shift. And you get a new Hudson-Berg matrix, H2. Now, as far as speeding up convergence, this works. This gets the job done. So when we have real or complex eigenvalues, you can get that quadratic convergence. Of subdiagonal entries going to 0 for a real or complex eigenvalue. So you can use this whether the shifts are real or complex. But the big but here that I'll actually spend the rest of this lecture addressing, okay, you don't actually like to do complex arithmetic. Or as I say ever so crassly, complex arithmetic bad. Because complex arithmetic is more expensive. First, in terms of storage, you're storing a real part and an imaginary part. Therefore, addition and subtraction will take twice as much time, twice as much space. Multiplication and division, even more expensive. You can pull off complex multiplication in like 3 real value floating point operations if you do it carefully. And division is even more of a pain. So even though the order of complexity of your algorithm is not going to be affected, you're doing a whole lot more arithmetic that you'd like to avoid. So we try not to do complex arithmetic unless we absolutely have to. There's a significant cost to it. Because what we can do is if we can stick with real transformations, real operations, and get a real matrix that is quasi-upper triangular with 1 by 1 or 2 by 2 diagonal blocks, then it's okay to do complex arithmetic just to extract those eigenvalues at the very end. That costs practically nothing compared to what we're already doing. But we'd like to keep it at that. And when John Francis developed the QR algorithm back in the 60s, this is what he went to a lot of trouble to do to avoid this complex arithmetic. Okay. So that takes us to the double implicit shift strategy. All right, so where the double implicit shift strategy comes from is the fact that if we look at U1 and U2 and then R1 and R2, these QR factorizations, so both of these are. If we put them together, then we get something useful. So U1, U2 times R2, R1. Okay. So now each of those matrices individually is generally going to be complex. But let's see what happens when we look at this product. Now, first of all, U2, R2, I have down there. So I can fill that in. That's H minus mu2 identity. Then I have R1. So then I can go ahead and distribute U1 H R1 minus mu2 U1 R1. Oh, wait, that's H, whoops. That's an H1 down here. Therefore, okay. Yeah, we only work with the original H in the very first step, our first QR factorization. So that also H, whoa, I knew something was wrong. 1. Okay. So now what I can do is here I can replace H1. H1 is R1 U1 plus mu1 identity. And over here, I have u1, r1 can be replaced by h minus mu1 identity. Okay. Oh, and I still have an r1 out here. So now I can write this as u1, r1, u1, r1, so it's squared, plus mu1, u1, r1, minus mu2, h minus mu1 identity. Okay, and wherever I see u1, r1, that also is h minus mu1 identity. Okay. Let's see. Okay. Now I expand like crazy. So I get h squared minus 2 mu1h plus mu1 squared identity plus mu1h minus mu1 squared identity, which will cancel with this one over here. And then I have minus mu2h plus mu1 mu2 identity. Okay. Yeah.
Over here, when for H2, H1 equals, you had the second one, do you see it? Yeah. You had mu1 times identity.
Yeah.
But for H2 you didn't. I mean,
yeah.
I didn't know if it was necessary.
Oh, yeah. Well, certainly in MATLAB world it is, because if I were to put it like this in MATLAB without the identity, it would think add mu2 to the whole matrix.
Right, rather than just the
diagonal. Yep. Alrighty. Okay, so now I can condense this a little bit more. So like these terms combined, so I have h squared minus mu1 plus mu2 h plus mu1 mu2 identity. Now, if we assume that we're dealing with complex shifts, because we're dealing with a real matrix to begin with, mu1 and mu2 are complex conjugates of each other. So this would be, so I'm going to assume that mu1 is equal to some complex number z, mu2 therefore is z conjugate. Therefore, mu1 plus mu2 is twice the real part of z, and mu1 times mu2 is absolute value of z squared. So, even though u1, u2, r1, r2 are complex, this matrix is real. Also, this matrix, u1, u2, is unitary. So, so it satisfies this property. This product with Hermitian transposes identity. And R2, R1 is upper triangular. So what that means is this product right here is the QR factorization of a real matrix. So even though the four matrices in that product can be complex, that means that U1, U2 and R2, R1 are real. So those pairs, those products of those two matrices are real to make the whole product real. Because of the uniqueness of the QR factorization. So this gives us a way to avoid complex arithmetic. But before I explain what it is, I have to go back here, because H2 is from working your way back through all these transformations, it's that same unitary matrix, U1, U2, Hermitian transpose H, U1, U2. So that's why the matrix U1, U2 is of interest to us, because it is the similarity transformation that carries out those two iterations. So, in other words, now we have another way to get the same transformation using only real arithmetic. So now I can tell you what that is. So what we do is first, I form this matrix M, that is H squared minus 2 real part of your shifts, H plus absolute value squared times identity. All right, so that's a real matrix. Then what you do is we go ahead and compute the QR factorization of M. And we get these QR factors Z and R. Z happens to be equal to U1, U2. But we're not computing U1 and U2 individually, we're computing the whole product as a single entity. And we know that it's real. Then what we can do is overwrite H with Z transpose HZ. And that carries out the same similarity transformations that are implied by the two QR steps over there with shifts mu1 and mu2. We now have all this, and everything done here is real. Now, but there's one really, really, really bad thing about this approach. Because we've traded kind of a complex arithmetic for doing way too much work in real arithmetic. Because look at what we have here. We're taking a matrix and we're squaring it. It's a Hessenberg matrix. So this takes matrix multiplication, order n cubed floating point operations, instead of the order n squared that we had already gotten to by doing other things. So this won't work. Now, but the thing is, we're actually not going to really back up. We want to try to still do something like this, but in a smarter way, without explicitly forming M, certainly. Okay. So, what will save us, and so what really saved Francis's algorithm and made him famous, even though he didn't know it for about 40 years. He was not like the old math professor or anything. He was, I believe, he was in industry. You know, he did this on the job, and then he left the field of numerical analysis. I think he went to a seminary or something. I don't know. He did something completely different. So my advisor, Gene Gottlob, tracked him down in 2007, which was actually also the year that Gene passed away. And let him know, hey, you're famous. You know, one of the top 10 algorithms of the 20th century is credited to you. And he made some appearances at conferences and all that. So at least 40 years later or so, he realized he'd done something great in numerical analysis. Although I read somewhere that a similar algorithm was developed like independently of Francis around the same time, I think in Russia, because Russians have pulled off all mathematical innovations, they just haven't translated them all yet. So convinced of that. And it's not really surprising because all these algorithms build off of what has already been done and just make these improvements. Okay, so, whoops. Okay, so how do we use the implicit Q theorem to pull off what I wrote there, only much more efficiently? Okay, so here's what we do. We don't compute all of them. We only compute its first column. Now, since it involves the square of a Hessenberg matrix, and then you add a Hessenberg matrix and you add identity, it's only going to have 3 non-zero entries, x, y, and z. So that takes practically no effort to compute. So not even worth thinking about, really. Okay. The next thing we do is we find a householder matrix. I'll call P0. So that when you apply this to this column of M, you zero out all the entries except the first one. And the reason why we want that is, so P0 is the first transformation in a QR factorization of M. So if we were just going to go ahead and, hold on a second. Oh, okay.
See that you in the column.
Ah, okay. Okay. So if we were going to just go ahead and do a QR factorization of M, and we would normally use householder reflections to zero out subdiagonal entries, that is the first one we would use. Then the first column we've taken care of, and then we move on from there. Now, the next thing we do is we're doing a similarity transformation on H. So we go ahead and apply that first transformation to H. Now, with what I wrote earlier about what we eventually want to do to H, you really want to do this. Well, in doing this, P0 is the first transformation that we would use, the innermost transformation. So in other words, we've started the process. Okay. Now this matrix, H is Hessenberg, but after we apply these transformations, it's no longer Hessenberg. There's going to be at least some entries that have creeped below that first subdiagonal. Not a whole lot of damage, but something. So then what we do is more householder transformations. And we need n minus 2 of them, because for a Hessenberg matrix, the last 2 columns can be full columns. They're allowed to be. It's the other columns that need to have at least some entries zeroed. So we apply those transformations to this P0 HP0 to restore Hessenberg form. Although I'm saying householder, it doesn't absolutely have to be householder, because we could use Gibbons rotations also. Because in each column, there's only going to be like maybe 1 or 2 entries to zero out. So householder is way too destructive for that. I mean, you just have to implement it carefully. Like not do like a full householder transformation that's working on every row, just a few rows. Because your householder vector, that V that you get, is only going to have 2 or 3 non-zero entries. Anyway, so now Now, but the beauty of all this, the reason why this works is these transformations, P1 up to P minus 2, they don't affect the first row or column. They have to work on later rows or columns to do their job. So, what that means is the, okay. So now, if I gather up all of these Hausdorff transformations into one matrix, so I let Z bar equal P naught, P1, P2, up to Pn minus 2. So it's the accumulation of everything we've done to H. So what that means is, because P1 up to Pn minus 2 do not affect the first row or column, that means that the matrix Z from over there, from the forbidden QR factorization of a matrix I'm not allowed to compute, and Z bar, or actually, sorry, Z tilde is what I call it in the notes, Z tilde, have the same first column. And that's just a byproduct of what rows and columns P1 up to Pn minus 2 influence, or what they don't touch. Okay. But the thing is, Z transpose HZ and Z tilde transpose HZ tilde are both Hessenberg. Okay. So, and the thing is, H itself is the matrix coming in is assumed to be unreduced. So, since both of these are designed to preserve Hessenberg form, because this was H2, that based on performing 2 QR steps is known to be Hessenberg. And here, these transformations were chosen to make this Hessenberg. I'll call this H2 tilde. So because Z and Z tilde have the same first column and they both bring H to a different Hessenberg form, then we can apply the implicit Q theorem. Z and Z tilde are essentially equal. And H2 and H2 tilde are equal in absolute value. And both have the same eigenvalues as the original matrix because they're both brought about by similarity transformations. So we could just go with this. Using Z tilde, that we can arrive at efficiently, not without having to compute a second degree polynomial of a matrix. So this is called so all of this is a Francis QR step. Okay. So that's how we got the first algorithm to efficiently compute all the eigenvalues of a general square matrix, regardless of whether they're real or complex. That also avoids complex arithmetic. Okay. Now, so that really describes the QR algorithm. Now we reduce A to Hessenberg form H. And then we can use this double implicit shift strategy. Whether the shifts would be real or complex. It turns out that we never actually compute the shifts. Well, actually, we do. The shifts are computed to form the first column of M. That's the only direct role that the shifts play. And then, so there's some choice there in order to try to achieve as rapid convergence as you can. So we keep doing that until H is reduced to this quasi-upper triangular form where we can just read off the eigenvalues. So the last detail then is, what about the cost? How expensive is this? Okay, so it depends on whether you want, okay, I'm going to make a chart here. Depending on whether you want just the eigenvalues, or you want the whole Schur decomposition, QT, Q, Hermitian transpose. So if you just want the eigenvalues, a Francis QR step takes 10 n squared floating point operations. We knew it would be n squared because of doing QR factorization of a Hessenberg matrix. Now, if you want the rest of a Schur decomposition, you have to add on another 10 n squared operations to accumulate all the similarity transformations that you're performing to get your Q. Now, the entire QR algorithm, now it's hard to say specifically, it's just an estimate, because you don't know how many iterations you're really going to need. It could be a lot better or a lot worse, but generally around 10 n cubed floating point operations. So same order of magnitude as the Gaussian elimination, but 30 times many floating point operations. And then an additional 15 n cubed if you want all the transformations, because you're accumulating all the transformations that made a Hessenberg, and then whatever transformations are accumulated during the iteration. So that adds up to quite a bit. Now, at the end of this, you have the eigenvalues and then you have a Schur decomposition, but you don't have the eigenvectors unless A is a normal matrix, in which case the Schur decomposition gives you those eigenvectors. There's a whole other algorithm called the Bartel-Stewart algorithm to use to get the eigenvectors, and that's a whole lot more expensive, and I won't go into details of that now. In the case where A is symmetric, getting the eigenvalues only takes order n floating point operations per iteration, because you're dealing with a tridiagonal matrix which is symmetric in Hessenberg. So all of your Gibbs rotations or household transformations take a lot less work. I don't have the figure handy for what goes down here. Okay, so that is the QR algorithm. It's actually, I learned about this during my first year at Stanford when I took a class that was all about eigenvalue methods. And I learned this out of Galvin Van Loan, which of course was the textbook, because that was Gene's house back then. And it was learning about these methods while studying for my qualifying exams that really made me interested in numerical linear algebra. Even though I was a PDE person and I've continued to be, that I take a lot more interest in numerical linear algebra than a PDE person normally would, because just the manipulations are so much fun to digest and or try to develop yourself for other problems. And things just have a way of working out magically. So hopefully I was able to at least somewhat convey that to you guys. What I'll cover on Thursday is the algorithm for computing the SVD that Golub and Gahan developed, and that's really what Gene was most famous for. That also has some pretty ingenious transformations to adapt methods for computing eigenvalues to computing singular values, because computing singular values of A is equivalent to computing the eigenvalues of A transpose A, and then you take the square roots. Now you don't actually do that; that's too expensive. But so they developed a slick way of doing that without performing these matrix matrix products. Okay. Questions? Questions about homework? We have time, which I didn't expect.
I'll work on homework for the rest of the class.
Okay. Well, I guess it means I can pick up my new computer earlier. What?
They brought you a new one?
You
already bought one.
Yeah, I figured about the help. It'd be nice to have my own. And then if they really are able to fix the other one, then I guess that's a backup.
Old school was giving you a new one.
Did you get another Mac or did you get a PC?
I'm sick of a Mac. Yeah, I was a PC person until 2015.
So late in the game.
Yeah, but so many of my students have Macs. I think definitely the overwhelming majority do. And I thought, well, maybe there's something to it, and then I can relate to what they are doing. So, but the thing is, Macs tend to last a whole lot longer, but not with me. It's taken a beating.
So was it new? They bought a new Mac for you? For example, if you...
Oh, as opposed to like refurbished or something?
The one that kind of is not working anymore.
Yeah.
Was it new in the beginning? Maybe it was secondhand.
I have no idea. Well, I hope it was secondhand, because otherwise I'm pretty embarrassed.